Well, let's go ahead and get started today. I guess we'll talk about the ethics paper later. Today we're going to talk about floating point. I started to touch base on this last time, but we're going to go ahead and do a review. Floating point is very important for, well, a lot of different applications. One is scientific simulations use it, but also a lot of your banking software will use floating point as well, which can be very important. Banking.
Oh,
Banking. We're all hearing bacon, so we're all hungry.
I can tell. I should have brought some donuts in or something, right?
It's Valentine's Day. Like, come on. You go to Krispy Kreme, they probably have like heart-shaped ones or something.
What? Chick-fil-A has like heart-shaped.
Oh yeah, like the heart-shaped boxes.
Wow, I didn't
Yeah,
even...
but the chicken minis are
So my students are going to give me more flack for Valentine's Day than my wife. This is amazing. Okay. All right, so floating point. So far we've used integers. We're now going to try and represent any type of decimal-based system. And yeah, we're going to talk about how it's implemented in hardware, how it's implemented in hardware, why we made the design choices, and of course limitations of floating point, which are very important when you have to utilize it. And of course the performance of floating point is very important as well. So, where does floating point come from? Well, first off, usually it's for scientific calculations, so of course naturally they want to stick with some type of scientific notation. If you notice up here, they start talking about something called the normalized form. And y'all have hopefully done this before, where in scientific notation, normalized form, you have one digit to the left of the decimal, and then all your other digits afterwards time 10 to raised to some power, which tells you the magnitude of the number. So if you look at this from, I guess you want to do a big evaluation, this is the precision, or what the exact number is, and then the exponent part is the magnitude of the number. The bottom two are not normalized because they don't have one digit to the left of the decimal. And by one digit, I'm saying, not 0, some digit 1 through 9. And also, this is not normalized because you have multiple digits to the left of the 0. All right, so this is base 10. This is what we operate on because we're used to a base 10 system. Naturally, a computer is base 2, so if you were to do the exact same thing in a computer or a base 2 system, it'd be, you still have your assigned bit, and then be 1 dot, and then your precision bits times 2's raised to some power. Now, in normalized form in binary, is there always a 1 right there? Yes. Why?
Because you have to have some number that's not 0.
And so your only choice is 1. Okay. Right. Whoa. So, we can basically imply a bit or get an extra bit of precision from this by stating that this bit is always 1, and we're just going to store the basically the decimals after that 1. So we don't have to store that 1, we just store all the ones over here, and those are x's, and then we need to store the magnitude, of course, as the number. And what's the third thing we need to store? So we need to store the precision, the magnitude base 2, and the,
Plus or minus.
there we go, the sign. Good job.
We got 2 for 2.
You got this today.
You should come early.
Yeah, you should come more often.
What's going on?
Oh, you're sitting in the front of the class.
Oh, that's why.
That's it. Okay. All right. Now, normally, so far you've used it. We have floats and doubles. Do y'all remember the difference? And the difference is? You said yes. So you walked right into it.
Yeah. I want to say double has more reserve space, right?
Right, reserve space. So how many bytes are in a float?
16.
8. Well,
All right, keep throwing numbers. One will hit, right?
1.
128.
4 bytes or 32-bit. A double. So if a float.
8.
Oh, good. Nice. Well done. Well done.
Double's just double floats.
Yes, that's
Double
it. Double the size of a float. Right. All right. Now you see where those numbers come from? Yeah. All right. Okay, floating point. By the way, floating point was not standardized until 1985. That means if you use computers before 1985, it may have different types of floating point representation that's different than what we are going to go through today.
Don't use a computer before 1985.
Well, you may not have that choice. For example, if you work in the military. So yeah, standard 1985, which was actually kind of late, especially since a lot of scientific applications were developed in the 60s and 70s. But it was developed because there was a huge divergence of different representations. People would not agree on what to do. So now they came up with the standard, almost universally adopted. Nowadays, the only time they don't use this standard is in the graphics card will sometimes have their own representation of floating point. But it's really more that they're going to use 16 bits instead of 32 bits to do floating point. So it's basically the same thing, just trimmed down. So single representation, that's floating point. Single precision, 32-bit. Double precision, 64-bit. All right. All right, so this is the standard of how, of what it looks like. You have the exponent and the fraction. Now, the exponent is going to be used to determine the power, 2 raised to what power, and the fraction is basically the precision of the number. It's how precise or how close we can get to the decimal approximation. And then you have your signed bit in the front. 0 is non-negative and 1 is negative. So 0 meaning non-negative, aka it could still be 0. But 1 is definitely negative. So 1 bit for the signed, and that's both in single precision and double. Then your exponent will either have 8 or 11, depending on your float or double, and then your fraction will have either 23 or 52 bits. Since the significand is always normalized, we always pretend that there's a pre-binary 0.1 bit, so you don't need to represent it. We call this the hidden bit. This is what I was talking about earlier. We don't need to store this guy because that 1 is always there. There are a couple of tricky things here. I think the first thing to point out is that the exponent is actually represented as an unsigned number, so from 0 up to how many bits? So 8 bits, that'd be 256. 11 bits would be 2048 or 47. But they're going to subtract a bias, and that is built in to what standard you're using. So the single bias is 128, and this is just to imply how you are representing a negative, or not negative, a negative exponent. By the way, if the exponent is negative, what does that mean the number is?
Decimal.
No.
Decimal. Yeah, fraction. Right. It's a fraction of.
Is a decimal.
AKA, it's less than 1.
Yeah.
Right. It's less than 1. But if the exponent's positive, then it's at least 1 or greater. Is usually what's going on. Okay. I think this makes a lot more sense if we have examples. Great. Okay. Last thing before we go into examples. Exponents of all zeros and all ones are reserved. So usually that's reserved for a very special case. They're not going to tell you, but usually it's if you're trying to represent 0 or if you're trying to represent infinity. Once the number gets too big, it just says it's infinity, and then, oh well, so much for floating point. It's too big. So the smallest value is an exponent of 1. So the actual exponent is 1 minus 126, which is a negative 126. Fraction can be 0. Significand's 1, so this means that the smallest number is 1 times 2 to the negative 128, or that number, 10 raised to the negative 38. Yeah, you can try and, basically it's 0 followed by 37 zeros, 1, 2. Largest value, again, all ones is reserved, so if you do all ones, the last one's a 0. 254 minus 27, positive 127, all fractions, which is close to 2.0, not quite, just under, which comes out to 3.4 roughly, followed by, 37 zeros. Okay. You see what the how this bias is working out? It just helped. It's an unsigned number, but you subtract the bias so you can calculate if it's a small fraction or a large number. So floating point, positive, 37 digits, or power of 38, I'm sorry, or basically 37 digits, or, oh wow, man, I cannot speak today. I'm just trying to say the numbers are between these two. Let's stick with that. All right, double. Obviously, it should be a little louder or a little larger. Louder. Louder. Way louder. Morning. This time, if you do the math, remember you're subtracting with the bias on double, it's 1,023. So 1 minus 123, you get negative 1,022. You do the math. What was it? Dot followed by 307 zeros and then 2. Hopefully, you don't need anything smaller. He agrees completely. Largest value, do the math again. Yeah, so it's 1, 8, followed by, looks like 307 zeros again. Hopefully you don't need anything larger. Okay, so that's the range of numbers that it can represent. The next one is talking about precision. And this is the actual numbers that it can show. Now this doesn't make too much sense, I don't think, until you see an example. So hopefully we're going to go to example, please. Oh, good.
Please.
Please. So how do we represent negative 0.75 in floating point? Okay. So first off, we need to convert it to base 2. Go ahead. No.
Oh, sorry.
It's okay. Notice, if you think about 0.75, what is that if you're trying to add up fractions with the power of 2? And that's what you need to think about when you are calculating these numbers. And what are these fractions I'm talking about? Well, you have 1/2, 1/4, 1/8, 1/16, aka 1/2 to the first, 1/2 to the second, 1/2 to the third, 1/2 to the fourth, ... So you're trying to decide if you need to add all these up. Has anyone done the series where if you add the whole I equals, we'll say 1.
We do that in Calc too.
Yeah, to n, where 1/2 to the I.
Sure.
Yeah. What does that converge to?
Is it almost 1?
Yeah, the limit as n goes to infinity. Yeah, it's 1. So it converges to 1. So the idea is all these could eventually sum up to 1. You have that implied 1 bit, so that can make it almost 2. Is the idea. Okay, so 0.75, hopefully you can see that that is half is 0.5, and then then you have 125 left over, so it's really just a half plus 1/4, right?
Mm-hmm.
Okay. Now, the first bit is implied because remember we're having that hidden bit, so really we just need to store the 1/4 and then make our exponent represent the correct calculation. So that's why we're saying it's 1.1 base 2 times 2 to the negative 1.
Sure.
Sure? Confusing? Okay. So we have negative 0.75. Obviously it's negative, so we're just going to have negative 1 times, and then 1.1 times 2 to the negative 1. Remember, 1.1 is the base. So this is, or the exponent. So it's 1 plus 1/2 times 2 to the negative 1. So it's, what, 1.5 times 2 to the negative 1 means you're dividing by 2, which is what? 0.75, which is what you're trying to get, right?
Okay, so the 0.1 to do is the 1/2.
Say that again? Huh.
For the 1.1 with the 2 on the bottom, that's
Base 2.
okay.
Base 2.
The decimal point you drew is a perfect circle.
That's good, right?
It's like 105.
No, we just gotta work on getting that larger.
Why is okay?
Is that better?
Why is 1 point? Why is it base? Why base? Okay, hold
Why? What's the question?
on. 1.1. you said
Base
that's
2.
Okay, base 2.
Yeah, it's confusing because you're used to using base 2 numbers that are not decimal. Now that they're decimal, you either have 0
Oh, that's
or
right,
1.
1 over 2. Okay, just 1
Yeah,
over 2. Gotcha.
yeah, because you're using decimal now, and you're trying to convert it back to binary, back to decimal or base 10. Yeah. Okay, so hopefully you see how negative 0.75 is equivalent to this base 2. So your fraction, if we make it all ones, we have to add, well, I'm sorry, 1 followed by a bunch of zeros, because remember these are basically representing 1/2, 1/4, 1/8, dot, 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 dot. So we only need the half, which is really just this guy right here, because this first digit is hidden or implied. So we only need to represent the first one because the offset is -1. So, exponent's -1 plus the bias, which is 126. So that's going to be our, let's see, our exponent. And then we already have the fraction part. And then you just plug that into the format we had earlier. So, let's go ahead and do this in reverse so this makes some more sense. The sign bit is 1 because it's negative. Everyone good?
Mm-hmm.
All right. So here's the exponent. What is that? That should be a 126 if you did that.
Sure.
Sure? Yeah. So 126 minus 127 is -1.
Oh my God.
And then
That's your.
yeah, that implies that it's 1.1 base 2. I mean, you could do 0, 0, 0, but times 2 to the -1, which is right here, which is what we were doing up here, and we showed it's the same as -0.75. Okay. Let's go ahead and jump back. Now I think this will make a little more sense. If you notice, the fraction part only has a certain number of digits, which implies that towards the end you can only represent so much precision with the fractional part of a floating point number. So that's what we call the precision of the number. So with floating point, you have about 26 bits, or 23 bits, sorry. And that comes out to about 6 decimal digits of precision. A double, you have way more, 52, and that comes out to 16 decimal digits of precision. Y'all kind of understand what I'm getting here? Yeah.
More precision with the double.
Right. Now, let's go back to the very beginning format, because notice something here. So the sign bit is always 1 bit, but when they doubled the number of bits, they didn't double the exponent, they more than doubled the fraction part. Why do you think they did that? I mean, because they could have made the double, right, 16 bits right here, and then that would be what?
A lot.
47 right here instead?
We want a greater precision.
Right. Why do you think greater precision is more important?
Because you want your computers to be accurate.
Computers to be accurate. Well, why don't they put more bits in the exponent? That's the question.
And which one are you storing? You're storing you have to store both the exponent and the fraction.
You have to store the sign, the exponent, and the fraction. I'm just asking the question, why didn't they reserve more bits to the exponent when they doubled the size? Because they could have. But they didn't.
But then that takes away from the fraction.
Takes away from the fraction. Right, and so the point is they valued your precision over the range here. And for scientific calculations, if your range gets too big, you can just store that off somewhere else and just use your magnitude you just worry about that later in your final number. But your precision is not something you can really code around easily. So that's why I believe they chose to put more bits into your precision than your
If your
exponent.
numbers are too large, you can always break your numbers down, do your calculations.
We can always store an
Smaller.
integer to represent your
Right.
exponent, right? But to do it for your fraction part, that's going to be very tricky. So I think it makes a lot more sense to put more bits towards your fraction. And I'm sure they had a long debate about what the exact bits should be, but they
That's why
eventually.
it took until 1985.
Yeah. Well, yeah. Y'all have never been in a standards body before. It's well, people have way too much, I guess, to say about things. And after a while, you're like, okay, whatever, let's just do this. Just get something going, please. All right. Okay, so let's continue on with another example. They're actually going to give us a floating point number and show you the representation. So the first bit's on, so it's obviously negative. Then you have, your next number is the exponent. That's down here, 129. And then the rest is a fraction. So -1 to 1, because that's your sign bit. And then your, what do we got here? Fraction. Wait, that's not a fraction. What's that?
You used an F instead of an E.
No, that's a, I thought I heard something. So your,
Oh.
Yeah. Here.
I don't know what an FX exponent is. That would be interesting.
The exponent.
It's for movies.
So the fractions here, notice that hidden bit is, the first bit is implied, so we have 1 plus 0, 1 base 2, all the rest are 0, so we stick with that. Times 2 raised to our bias, which is 129 minus, our exponent, 129 minus our bias, which is 127. This in decimal, hopefully you can see this is 1/2, and then that is 1/4, equals 1.25 times 2 raised to the second power. So that comes out to 5.0. How are we doing?
Alright.
Doing okay? All right. Let's see, some addition. Okay.
Say the 0 was 1/2. Oh, that was position for 1/2. Never mind.
Yeah. So this represents a half. This represents up to the second power, or a fourth.
And then at the bottom, 1 plus a 4 is just 1 point.
Because the 1 is always there, because
Yeah.
to be normalized, you have to have the 1.
Yeah, okay.
Yay.
Yeah. Yeah. All right. So consider the 4-digit number 9.999 times 10 to the first plus 1.60 was 61 times 10 to the negative 1. Okay.
Gross.
So if you want to add these, you want to shift with the smaller exponent. Namely, you want to shift everything to the largest exponent. This is terribly written comment, but you want to make everything equivalent to whatever the largest exponent is.
Sure.
Then you add the significans.
I'm just typing in your calculator.
Typing it. Well, yeah, but you're writing the hardware now, Caitlin, so you have to figure out how's the hardware do this. You add it, you realize, oh wait, that's not a normalized form. You have to renormalize it. But in this example, we're saying we have a 4-digit decimal number. We can only store 4 digits. This has a 5th digit. So we have to round and renormalize if we need to. We're saying we can only store 4 digits. With floating point, you can only store 23, technically 24, 2-bit digits, or 1-bit digits. So then in this case, they rounded it to 1.002. So notice that there is some rounding going on in your hardware. If we were to digit a 4-bit binary number, now hopefully you can see this can be carried on to 23-bit if we're using floating point, or 56-bit in double? I never remember. Whatever. 1.0 times 10 to the negative 1. What is that? Quick guys, what number is that?
Never mind.
Is this supposed to be like instinctive?
I'm trying to make it instinctive.
Okay. Yeah, this is not going to be.
What's 2 raised to the negative 1?
1/2.
1/2.
Yes.
And you multiply by that by 1, what do you get?
1/2.
There we
Yeah!
go.
See, it's not hard. You just need to sit down. So this is 1/2 minus, oh boy,
Oh no.
That's a big jump.
Gotta
Well,
ease
it's
us
2,
into
so it's 1. Well, I don't know why I did that. I made it even
Oh.
grosser. 1 plus 1/2 plus 1/4, which is what? 1.75.
Yeah.
What's 2 raised to -2?
1/4.
All right, so it's 1.7 times 0.25, and you can just do that in your calculator. You get 0.4375. I forgot to put the negative up here. Okay, but I'm just trying to show you that this is the addition that we're trying to do. First, you align the binary points, so you raise everything to the highest power, which is -1. So notice you have to shift that down. You understand this step? You want to make sure the
That's the one
exponent.
step I do understand.
All right, make the exponents the same by raising it to the highest. Yes, Carl? You sure? Okay. See, he's just trying to help you out.
He's hissing at me.
He's hissing at you? I think he thinks you should know more. That's all. All right. Sorry. Significance. So we're going to add, aka these two things. And this is binary addition. So notice when you add them, we get that.
Yeah.
Oh yeah, because we have this
Just
negative.
making questions.
I was like, wait, how did that happen? Oh, there's a negative side. So that whole 2's complement, yeah, 0.001. Now we need to normalize. We need to move
Two
this
exponent.
1,
for the middle
2,
one.
3.
Yeah, I was just.
That exponent was done very poorly. It's
Which
just
one?
a regular sized one.
Everyone's a critic here.
Just always having issues with slides.
Normalize. So notice you had to move the 1 over 3 times, so you had to subtract 3 from the exponent to get -4. You okay with that?
Sure. Oh, we're going
Minus
from
3.
that step to the other step. Okay. That way.
Man, this writing on the board really
That's
really
minus-
helps. Too bad the people online just can't tell.
You mean our later selves?
Yeah, or later herselves at 2 a.m.
Future us.
So then you go ahead and you round and renormalize. Luckily, we don't have to do anything. What's that?
I said
I
I
would
would never
never-
be up at 2 a.m. doing this.
Yeah.
No way.
If I ain't got it figured out by midnight, I'm just gonna go to bed and I'll wake up tomorrow and do it.
And midnight's pushing. It's
Yeah.
about 10 o'clock.
Y'all ever you start your programming projects at 10 p.m. and see?
No.
Good.
No, I never did anything
No.
like that. Even
No.
for data
No.
structures, I never did anything.
Yeah,
like
what
that.
you did, Dr.
Alice, and please
I mean,
proceed
data
with class.
structures, we did some crazy times.
Okay. All right.
Senior project 3 a.m.
Any questions on this example? Is it intuitive now? But do you think you can figure it out?
Maybe.
Maybe on your homework
Google help.
that I've assigned.
Some Google help.
That's from Google Help. That's from the book.
Oh, great.
But this is on the homework now?
Yeah, this will be part of your homework.
This is already on the homework?
Yeah, I have assigned homework
Yeah.
today. We'll go over it.
Oh, you're assigning homework
Wait,
today
is this
too?
the third homework?
Yes.
Oh,
Wait.
man. Wait.
We're getting another one assigned today?
Yes.
So,
Oh, no.
last time you
Yeah, no.
assigned the homework, and it was like a
4
number,
things. for this class.
dot, but the dot was like at the bottom, another number.
We'll go ahead and ask me when we get there. Let's figure out floating point first. All right. We're going to erase this.
I don't know what I'm working on today. I need to study for that.
Okay. All right, guys. So now that we know how floating point works, who's ready to do this in Verilog? Oh.
Oh, that still exists.
Maybe if you gave me
Examples.
a template, I'd be solid.
I'm not going to ask you to do it in Verilog.
Thank God.
Oh.
Yeah, floating point's actually really annoying to do.
Floating point's annoying in general.
So, much more complex than an integer adder. Hopefully, y'all can tell. Actually, you seem to understand that once I told you let's do this in Verilog. Doing it in 1 clock cycle would take way too long. So even doing an add does not happen in 1 clock cycle.
Wow.
So a slower clock would penalize all instructions, so it usually takes several cycles, and it can be pipelined. Have we talked about pipelining?
Yes.
Yes, excellent. Oh, good, we have a picture. So I'm not going to ask you to do it in Verilog, but you need to at least understand what this diagram is telling you. So this is... Who said that? That's great. Good. So what part of this is so magical?
It's huge.
It's huge? Well, we're just doing addition.
It's huge. It's a
So,
lot of hardware.
A very convoluted way of addition.
Just saying.
It's a lot of hardware.
wow, this is a lot of complaining.
It's going to take up a lot of space.
So you have two numbers that you wish to add. Notice we are breaking it down into 4 steps. Does it tell us the 4 steps? No. Okay, great. Step 1, step 2, step 3, step 4. So it kind of
Sort of tells.
yeah, it sort of tells. So you're going to first compare the exponents. Notice you have your exponent here and your exponent here. It goes to a small ALU to tell you the exponent difference. And this is just, if one is bigger than number, what does it need to be moved to? The control reads that in, and then it's going to set, notice that these 2 bits, to shift one of the exponents. Notice that both, what is that? Oh, this is going to shift the fractions, actually. Notice both fractions are going to these 2 pieces. Depending on who needs to be shifted, it's going to go here because he's going to be shifted to the right. And who doesn't need to be shifted, let me try it, goes over here. So the control line tells which one is just going to be forward to the big ALU and which one needs to be shifted. That's step 1. So step 1 is shifting the fraction. All right, okay? Step 2, add. Because that's a lot of bits to add, a lot of bitness.
Yeah, big ALU.
So it's a big ALU, yeah, it's as opposed to a small one. So that's just adding. You add the fractions, okay? Now you need to normalize. So the answer from the big ALU is might be shifted, and what else is coming in here? The exponent. Wow. Oh, the exponent's coming in here as well. In case, and the reason for this is that if it's in the big ALU and your answer becomes, 0.000111, well, that needs to be shifted left or right. And then the increment or decrement also needs to be added, or at least so increment or decrement of the exponent, so it knows which exponent needs to occur. Because remember, when you're back here, step 3, right here you didn't have to round, but over here, well, you still didn't have to round. Oh, that's nice. Oh, yeah, you did. Notice right here, you had 10.015. So you need to round down, or I'm sorry, you need to normalize, You need to normalize by shifting it to the left, therefore adding 1 to the exponent. So over here, you may have to shift to the left and then increment or decrement the exponent accordingly. So remember, that's normalizing. That's all it does. Last thing that happens is rounding. This one can be a little tricky because you notice it feeds back up to incrementing or decrementing. But basically, if you have that 0.15, if it ends up having to shift your exponent again due to rounding, then it needs to do a shift again and increment, and then you finally have your final answer at the end. All right. Any questions? So notice that a standard integer addition takes 1 cycle or 1 step, and this one takes 4. Ew. I mean, that would be the gross, right. But this is very important for scientific notation or computations, so we do it.
We do it for them.
Well, and for banking software.
Eh,
All right, how about multiplier? Who's ready for multiplying?
Well, that escalated quickly.
All right.
No big
It's
deal.
similar in complexity to the FP adder, but uses a multiplier for significans instead of an adder, aka you have an adder, you have a multiplier over here, and then your rounding and normalizing hardware is more complex because things can shift a lot more. Did I need to bring like coffee and soda for you, Matt? Okay.
Not so
Coffee
just
and
coffee.
soda?
Just coffee.
Just coffee? You sure? I don't like the taste of coffee, so you need something to wash that down. Yeah.
Coffee's
Yeah.
Hmm?
What's a tea for?
Coffee's wonderful.
Yeah.
Okay, I got tea.
Cheese, but-
I'm drinking tea right now.
Yeah, I'm
good.
good too.
I'm drinking tea.
Are you?
Usually what happens is your FP unit is going to do addition, subtraction, multiplication, division, reciprocal, and square root, because some hardware decide to do square root inside of one, I guess, block. Because if you notice here, your ALU can do basically what it needs to, and then you can have a complex normalizer and rounder afterwards. That should be standard, whether it's addition, subtraction, multiplication, division, or whatever else.
So because they don't need to duplicate, the ALU can be used for all.
Right. The big thing is the ALU just needs to be able to handle adding, multiplying, dividing, and the rest of this hardware may be a little more complex because now you're not just incrementing or decrementing. You might be incrementing by a large number, and then shifting, same thing. But it's going to be the same hardware after that. Y'all see the point here?
The
So luckily-
floating point?
What?
Like floating
The
point?
floating
Ha ha.
point.
Ha. Man, that was painful.
All right. You also have a way to do floating point to integer conversions. That's usually done in the hardware as well. Operations usually take several cycles, so it can be pipelined. You can see right here, after step 1 is done, you can go over to step 2 and then have the next floating point start back here. That's perfectly fine. Okay, great.